and I'm happy here to present you to the first speaker of today, this afternoon, Frank Tarazi, working for Bollinger & Grohmann since 2014. And you worked on numerous projects in Germany and abroad with a focus on steel, glass, and facade engineering, including new and refurbished buildings. Amongst others, you've been you're very proud of your work at the European Investment Bank in Luxembourg and at the Maritime Museum Lingang in China. So, without further ado, over to you, Frank.
Thanks a lot. Yeah, good afternoon. Don't be afraid about this lengthy title of the presentation. It's not going to be very scientific, so I'll do my very best you don't fall asleep after having your lunch. And I'm here to present more or less a case study, scaffolding called Reflections, that was built in Paris. And the authors of the paper are my Paris colleagues, Nicolo, Paul, and Klaas. And unfortunately, or fortunately, I must say, they cannot be here, but asked me to present the project to you. So it's my first time being here at GPD, and I've never been on such a huge stage, so we'll see how it works. There are a lot of empty spaces yet, but I'll do my best. So here it is in all its beauty. We have been asked by an artist, Barrois, Emmanuel Barrois, who came up with the idea to do a scaffolding with glass elements. And the idea is that it's a modular system that can be put together, dismantled, put together again at a different place, and obviously it's a piece of art. It's not a structural scaffolding, but it's a nice study on how to solve the different problems that are involved with the detailing, and also on a global level, how to deal with the predictability and also with the brittleness of glass. So these first two impressions, you see at the bottom there's a steel base, and up from there it's all glass. And the idea was, there were many studies done on the layout, on the configurations of the diagonals, maybe have some fancy shape, but the decision was taken, okay, we should stay very clearly in a pattern that everybody is familiar with a scaffolding. And so there were also a lot of studies done on how to do the diagonals, in which configuration. And we ended up with this chevron shape. So if you're familiar with structural engineering, you would say, okay, why are there so many? We could only have one diagonal in every plane and every level. That would be sufficient. But of course, then the artist said, that's a little bit too, we need more. We need more diagonal bars. And that's where the dilemma starts. Having more than one diagonal in every level means that it's structurally indeterminate. So it's sensitive to movements. You never know, okay, where does the force go? How big is the force in the individual member? So that's the key thing that we had to obey here, how to do this project. What you'll also see, there is no diagonals in plan view. There's no spatial diagonals in these cubes. The cubes, by the way, are based on a 115 by 115 grid. So the whole thing is 460 by 460 in this upper part, and then spreading out to 6.90 meters at the bottom. Overall, the glass part is 12.65 meters high, which is supposedly the biggest glass scaffolding structure ever built. So this is the bar itself, based on the 115 module, and it's comprised of two layers of 19 millimeter annealed glass. Except for some bars, they consist of toughened glass. The long diagonals at the bottom, and some with the highest forces of the verticals at the bottom are also toughened. And it's laminated with EVA. And of course, the end connection is the part where the gluing takes place. So a lot of conceptual studies were done on how to do the nodes. And I've seen a lot of them. I only picked 4 out of these conceptual studies. The boldest one on the top, that would have been quite a challenge in my opinion, because this was considered to be all glass. So what you see there was considered to do this in glass as well, and bolt it somehow together, or glue. You can see that picture with the glue. So that would have been quite a challenge, and it was abandoned to do that. And then we stayed a little bit more conventional. At the bottom, you can see the three different configurations on how to do the interface between the node and the actual glass prism. And we ended up with something similar to that. That's a pre-study still, but with a glued connection of this adapter to the end of the glass. And so this resembles somehow what you're all familiar with, this Waxman node or the Mero system where you bring all the bars together. The difference is that we don't have this ball and you cannot screw whatever configuration into it, but it's all predefined due to the geometry and the location in the system. And on the right-hand picture, you can already see the stainless steel interface, this adapter, and the sleeve with the thread, and this laser welded node. So a little bit more in detail, on the right-hand side, you can see all the different configurations in these different colors that we had to provide. There's a M14 thread, there's the sleeve, and there's the counterpart on the node. As I said, laser welded. The shape of the angle, that was determined, by the way, Emmanuel Barrois, the practice, they did all the glass assembly, they did also the lamination and also the gluing in their own shop. And in the beginning, it was considered that we only have a 0.3 millimeter gap for the epoxy. Later on, that was changed to 0.6 millimeters due to the tolerances that are there. So 0.3 is really tiny. And there's one special thing that most of the threads in the horizontal and vertical bars, or all of them, are right-handed and right-handed. There's no left and right-hand thread. Only the diagonals have left and right hand, but only on one end, and the right hand on the other end. I'll get back to that later. So of course, we had to do all the structural analysis, come up with the relevant loading, which is obviously wind loading, because there's no people climbing it, hopefully. That's, by the way, it is placed in a water basin, so that prevents, hopefully, people from climbing. And what you can see here at the bottom, again, in this different color, that's the steel part, and above it's the glass part. And so the loading was derived by code, and also by Nicolo refers to this as the cookbook. So you don't get a meal from it, but it's from Mr. Cook. And so at the end, you have about 11.2 kilonewtons of tension in the red areas and approximately 15 kilonewtons compression maximum. And we took into account a little bit of the shading of the different levels of the truss. So it's a bit tricky to be sure, okay, on the load side, are you really safe or not? Is it really exactly what you're expecting? And then we went on, okay, to the design of the glass stainless steel joint and how to glue it. And the choice was pretty soon taken to use an epoxy, quite a high strength epoxy and rather stiff. And down at the bottom, you can see the standard values that they are giving for average lap shear connections with metals. We didn't have any numbers for glass to stainless steel, but we believed, okay, it should be somewhere in the range of this 20 to 25, 30 Newton per square millimeter. And then we did some calculations with a finite element analysis. And as you can see, the one on the left, that's for axial loading. So there's a concentration in the center with the bigger stress is there. And of course, that's due to the stiffness of the whole node. And then we also looked at what happens if there's a temperature load on it. And it's quite obvious the stresses are small in the center because that doesn't move, and towards the edge the stresses will be higher. So that's quite favorable because the areas with the maximum stress are not at the same points. So that's quite good for us. And however, with this kind of structure, we don't really rely on these calculations. We did a lot of testing. And the preliminary test was about adhesive itself. And it turned out that always the glass broke. It never failed in the adhesion. And of course, the next calculation is, we have to come up with a number how much the capacity in tension and compression is. And for the tension capacity, we came up with 35 kilonewtons. But that was only for the glass itself. It didn't take into account this complex geometry. And for compression, the buckling capacity, you can see the numbers there. For the middle length, the standard diagonal, it's about 15 kilonewtons. According to two different codes that we took into account, and also some shear stiffness of the interlayer, 5 seconds and 25 degrees were taken into account for the shear value of the interlayer. Because it's due to wind, so it's a short load and not a permanent load. So then we went on to do a lot of buckling tests, just to make sure, or to find out how good is it, and our calculation. And we came up with a much higher number. It's around 50 kilonewtons NRD. On the left and right side, you can see the configuration. Unfortunately, they put a pipe around it for safety reasons. I would have loved to have an acrylic pipe to see what's going on. So only afterwards you can see the pattern, the fraction pattern. And so the results were very promising. We did the same for the tension. And if you have in mind what I said before, the number, there's quite a difference. The tension results were quite lower. Here in this comparison, you can tell, okay, for buckling, we were much better in the test. Tension, much lower, but still way above design load. Comparing the buckling over here, that's really close, 14.2 to 14.8. You might feel a bit uneasy, but the test showed it was much better. And the reason for it, in our opinion, being that this buckling is a very short term loading in the test, and also we went all the way even after cracks occurred. But the calculation, that is, the limit is there's one crack in it. And then as soon as you reach the tension limit, that's it. So that's how we think this big deviation occurs. And here, as I said, this was only the bar itself, the glass, and it didn't take into account all the complexity of the connection. Then we also did the same for the temperature. We put this heat cutting knife to it and raised the temperature to 80 degrees, and nothing happened at all. There was no cracks, nothing in this location. The glass itself was at room temperature. So predictability, I have to go through that very quickly because we are already short of time almost. So our key goal on the one hand side, if you know exactly what force is in the member, that would be nice. But since it's hyperstatic, that's an issue. As I said, you cannot really predict exactly what load is in which member. Taking into account there are tolerances, there might be some slippage. And that's also a reason why we finally decided to do the connection in a longitudinal way. Don't do any bolts with some play in it. That would be very unpredictable what's happening. If you have it longitudinal with the threads, there's not going to be a lot of play in the connection. And so the key thing in our opinion in this case was we have to reduce the scattering to a very minimum to make sure the production is really high quality. We don't have any large deviations in the member length, so we don't cram a member into a position and have some inherent forces. That was our key goal. And so we decided to machine all the nodes. They were wax cast iron, stainless steel. And these are the numbers that we came up with, that we have to be in these confinements. So keep it as precise as possible. And also for the gluing, we used micro shims, really tiny. I don't know whether you can see that. Yeah, you might. There are these little dots here. So that ensured that the thickness of the epoxy was as it was designed and not totally different. Then we used jigs for the laser welding of the nodes, and all of the nodes were then 3D scanned afterwards, and those that didn't meet the requirements had to be replaced. So that's very tricky with these configurations, and it was also decided it makes absolutely sense to do a mock-up and try before going for the full size. It's real size, but only a little part of it. And there was also elaborate studies on tolerances and how to accommodate them, and how big they are and how big they could be. And during the mock-up construction, it turned out, okay, it's very hard to align two threads exactly in one line without any angle deviation. And so we had to come up with a different set of sleeves with a little bit of more tolerance in the thread. And so that was like a backup. And so when it's hard to turn, they could change the sleeve to another one that has a little bit of play in the thread. So that worked out fine in the end. Overall, it's about 1,200 bars, I forgot to say, in the whole thing. So there's a little video. Can I start it? I hope so. Of the assembly. So there's a jig, that bar that you can see behind. Then the sleeve in the beginning is all the way at the end. You thread it back a bit. And then on the other hand, you'll see there's a 2 millimeter gap to the node. And then, of course, it's a bit tricky because you have to make the threads meet one another in the right angle. So you see now he's turning it, and then the distance or the location is checked with a laser. You will see right away. And by pushing it a little bit, you can adjust it by 1 to 2 millimeters in the end. And on one end, then the thread, the sleeve is turned all the way against the adapter to block it. If you look closely, you can see these little holes. There were grub screws that wasn't intended in the beginning, but it turned out that we don't need them. And also the workers, they would go crazy because they're so small, they would drop them all the time. And so for this temporary structure, it was decided that this is fine. So here you can see it's perfectly aligned in the one direction already, and the other direction it can be this can be adjusted in the next step perpendicular to it. So discussion, yeah. So it turned out that we were able to install it within 2 weeks, the 1,200 bars, so that was pretty quick. And the guy installing it, they didn't have any experience with glass. It's just like a scaffolding people that are doing it. And of course, you had to figure out how to do it without blocking yourself and not touching the glass. And finally, when they dismantled it, it was there in the Palais Royal Gardens for 2 months. It underwent a medium storm as well, Cynthia. So after they dismantled it, we found a couple of bars that had cracks. And all of the cracks were in that fashion, but they were not like any specific location. We couldn't say, okay, this is the most loaded part, of course, that's logic. But they would be on the south, they would be on the north, they would be top, there would be some at the bottom. I don't know exactly the number of how many cracks they were. But now we can discuss, is this a failure? Is it a success or not? I think it proved the system it works. We have the redundancy on a local scheme because we have this laminated bar. And also we have in a global scheme because we have these redundant diagonals in the system, redundant bars. And I think there is some room for further research because discussion was going on. What's the reason? And I think this is quite a forensic thing to do, to find out what it is. Was it during mounting? Was it during the loading? Was it handling? Was it a preparation of the glass? What caused this? And to end my presentation, I just wanted to show you some more of these very nice pictures taken by Niccolo Baldassini of our office. It is very fragile. And at the other hand, and that's also something interesting because due to how we mounted it, we couldn't put all the bars in a certain rotation. And the artist was fine with that because this also creates the diversity in the structure. If it's all the sunlight is parallel, everything is in a exact same rotation, it would be quite boring in our opinion. So if they are twisted a little bit, you have a little bit of more play in the reflections. And also looking at it from different angles, sometimes it's really calm. And if you turn a little bit, it gets quite chaotic. You have a lot of bars. There's never an X. This is due to the fact that the bars, the diagonals are switching the direction in the different planes. So it was there for 2 months, and it was meant to be redone after it has been dismantled. It was meant to be redone in Rome. That was cancelled. But next year it's supposed to be built again in Paris, and after that it's supposed to be re-erected in Japan, which might be another interesting issue about, hopefully it doesn't get an earthquake during that time. But that would be the next level of testing it in real scale. Thanks.